Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever, and today we are continuing our exploration of exponentials with growth and decay. Let's get right to it, shall we? All right, so talking about growth, population growth can be modeled using exponential functions. Here's a real quick example we'll blow through here. If I got a population of 100 mice and their population increases by 20% each week, then their initial population, p sub 0, would be 100. And to find the population after 1 week, I would multiply by 100% plus 20%, or 1.2. So that's 100 times 1.2, whatever that is. And then, so I have that population, and then I would take that population, which is P1, and multiply it by 1.2 again, or the original amount, 100 times 1.2 squared, and so on, okay? So we can see then that we're going to have a pattern of after n weeks, the population of the mice is going to be 100 times 1.2 to the n. And they give us a nice smooth graph. And it is an exponential function because our variable is an exponent. Okay, so let's take a look at an example. An entomologist monitoring a grasshopper plague notices that the area affected by the grasshoppers is given by this function here. In hectares, where n is the number of weeks after, that's important, after the initial observation. So find the original affected area. Well, the original affected area is at week 0, like we haven't had a week pass, so we would find a sub 0. Well, that would be 1,000 times 2 to the 0.2 times 0. Well, that's going to be 2 to the 0, and anything to the 0 power is 1. So the original population is 1,000 grasshoppers. Bam! So there we go. B, find the affected area after 5 weeks. So A sub 5 would be equal to 1,000 times 2 times 0.2 to the 5th power. And I could crank this in my calculator and show you that, but I know you know how to do that. So I'm just going to give you the answer, and that answer is 2,000. And then let's see, after 10 weeks, so A sub 10 would be the same thing, except this would be a 10. So the 5 would be replaced by a 10, and we would crank it on our calculator, and that is 4,000 hectares. And then what do they want? A sub 12. Again, same thing. We would play, instead of a 5, it would be a 12. And that is 52. It turns out to be about 5,280 hectares. Okay, and they want us to draw the graph of A sub n against n. So I'm just going to get rid of this x and call it an n. And this is going to be my A sub n. And so I've got, let's see, out to about 12 weeks. So I'm going to say, let's see, this is 2, 4, 6, 8, 10, 12 weeks. So that's 12. And then how high are we going? We're going up to about 5,000. So we'll say 1, 2, 3, 4. That's 5,000. Okay. And at time 0, we were at 1,000. So 0, 1,000 is a point. At time 5, so that's 2, 4, 5, we were at 2,000. So that's about right there. And at time 10, right here, it's 4,000. Which is, let's see, 1. Oh, wait a second. 2,000 is up here, isn't it? 1. Yeah, I totally messed this up. So at time 0, we are at 1,000. At time 5 weeks after, so these are worth 2, 2, 4, 5, we were at 2,000. So that's right here. Then at time 10, we were at 4,000, which is right here. And then at 12 weeks, 5280, which is about right there. And you can see how we've got a nice, smooth, exponential curve. Okay. Next, we talk about decay. Well, as things can grow, they can also decay. And so there's another nice example where, what do we have? We got a radioactive substance. It has original weight 20 grams, and it decays by 5% each year. Well, if it decays by 5%, then the remaining weight after a year is going to be 95% of its original weight. So our multiplier is 0.95. And it's the same idea here. After the initial weight is 20 grams, and then after 1 year, it's 20 times 0.95. We take that total and multiply it again by 0.95, or the original weight by 0.95 squared, on and on and on, and we get a nice smooth curve going downwards. Okay. So we have a diesel electric generator. When it's switched off, the current dies away according to the formula I sub t equals 24 times 0.25 t amps, where t is the time in seconds after the power is cut. So that means that it's actually decreasing by 75% each second, okay, because our multiplier is 0.25. So for part A, find I of t when t equals 0, 1, 2, and 3. So for part A, I'm going to find I of 0. And if you look at this, I'm replacing the t there. So that would be 24 times 0.25 to the 0 power, which is 1. So that's going to be 24. Obviously, it should be that. Before you start, it should be 24 amps. Oh, they didn't tell us that. Never mind. So that's the initial the initial power that's going away, the initial amps. Okay, so then I sub 1 would be 24 times 0.25 to the first power, and that turns out to be 6 amps. So we have 6, and then same thing, I sub 2 is going to be equal to, instead of a 1, we would have a 2 here, and that's going to be 1.5 amps. And then I sub 3, I will tell you, is equal to 0.375 amps. Okay. What current flowed in the generator at the instant it was switched off? And I kind of already spoiled that. That is going to be 24, because that's at time 0 right there. C is plot the graph for t greater than 0 using the information above. I'm not going to plot it on here because it says use your graph or technology to find how long it takes for the current to reach 4 amps. Okay, well, let's go ahead and just graph it on our graphing calculator. Okay, so the original function is I sub 0 equals 24 times 0.25 to the t, but we have to use x. Okay, and there we have it. But I want to get a good picture of the graph, so I know that the initial was 25 or 24, so maybe I'll make this 30, and I don't know, we went out to 3 seconds, so maybe I'll make this 5 seconds. And then I really don't care about this, -1, -1, because everything's happening in the first quadrant. And then I don't like these tick marks. I'm going to make them all 1, I think. Let's just go here. Menu, Windows Zoom, Windows Settings. I'm going to make my X scale 1. Oops, I got to highlight the whole thing. And my Y scale, since it goes up to 30, maybe 5 would be a good choice for a scale. Then it's a nice clean graph there. Okay, and then the question, if you remember here, was use graph or technology to find how long it takes for the current to reach 4 amps. So realize what we have here. Our x-axis is time, and our y-axis is the number of amps. So to find 4 amps, I'm going to go ahead and plot A equals 2, or I of 0 equals 4, and then I can just find that point of intersection, because the x-coordinate will be the time it takes to reach 4 amps. So I'll go Menu, Analyze Graph, Intersection to the left, to the right, and I get 1.29 seconds. Okay, so part D is about 1.29 seconds. Okay, and I know it's not going to be exact just because of the nature of the equation. And on the calculator, I didn't have my decimals out to show you that it's more. This is rounded to 3 sig figs, but that is indeed the case. All right, last example. The weight of a radioactive material remaining after T years is given by W sub T equals W sub 0 times 2 to the negative 0.001 T grams. Find the original weight. Oh, okay. So to find the original weight here, we have to find, that's when T equals 0. Okay. So W of 0 would be equal to W sub 0 times 2 to the 0, because if I replace T with 0, this becomes a 0. So that's W0 times 1, which is in fact W0, which seems a little obvious, but they just are verifying that that is indeed the original weight. So they want to say find the percentage remaining after 200 years. So I need to find, for part B, W sub 200. So that is going to be equal to W0 times 2 to the negative 0.001 times 200. And if you work all that out, that is equal to W0 times 0.8706. So it's 0.87 times 0.8706 times greater than W0, right? Because this is W sub 0 and it's being multiplied by 0.8706. So that is actually the percentage increase. So after 200 years, it's about an 87.1% rounded to 3 sig figs. Or I'm sorry, the percentage remaining. I messed that up, so sorry. It is negative, so it is decreasing. So that's the amount of decrease. I misspoke, my apology. So there is 87.1% of the material remaining after 200 years. All right, so that'll do it. Hope you enjoyed it. I know I did. And with that, I am